Hello everyone, my name is Dr. Dipti Verma, Associate Professor, Computer Science and Engineering Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today, let's do a quick recap of our previous lecture on advanced image manipulation and enhancement techniques. Advanced image manipulation and enhancement techniques encompass a range of sophisticated methods designed to improve and transform images. These techniques include image denoising and restoration, super resolution using deep learning models, precise color correction and grading, high dynamic range imaging for capturing extensive tonal ranges, content aware scaling for distortion, free resizing, seamless object removal and manipulation, and innovative image synthesis. Approaches like deep dreaming. These methods find applications in diverse fields such as photography, design, medical imaging, and computer vision, offering powerful tools to enhance, refine, and creatively modify images, while leveraging advancement in artificial intelligence and deep learning for exceptional results. So, let's begin with the detailed understanding of today's lecture on geometric transformation in image processing using Python. Geometric transformations are commonly used in image processing to manipulate the geometry of an image. How to perform geometric transformations on real-time images using Python. Performing real-time geometric transformations on images using Python can be achieved using libraries like OpenCV. Install libraries. Make sure you have OpenCV installed. You can install it using pip install OpenCV Python, import libraries, import the necessary libraries in your Python script, import CV2, import NumPy as NP. Capture video stream, initialize a video capture object to capture frames from a camera or video file. Use 0 for default camera or provide video file path. Loop for real-time processing, creating a loop to continuously capture frames and perform geometric transformations. Perform geometric transformations inside the loop. You can apply various geometric transformations such as rotation, translation, scaling, and perspective transformation using OpenCV functions. Translations is a type of geometric transformation that moves an image by a specified amount in the x and y directions. We can use the CV2 WAP-affine function to perform translation. Complete code for translation using Python. Import CV2, import NumPy as NP, load an image, define the translation amounts, create the translation matrix, get the dimensions of the original image, apply the translation. Display the original and translated images. Replace path to your image.jpg with the path to your own image file. This code loads an image, applies translation using the specified dx and dy values, and displays both the original and translated images. Rotation is a type of geometric transformation that rotates an image by a specified angle around a center point. We can use the CV2.getRotation and CV2 WARP-affine functions to perform rotation. Complete code for rotation using Python. Import CV2, import NumPy as NP, load an image, define the rotation angle in degrees, get the dimensions of the image, calculate the rotation matrix, and apply the rotation using WAP-affine, display the original and rotated images. In this example, you can modify the angle variable to rotate the image by a different angle. Additionally, you can adjust the rotation center to specify a different point around which the image should be rotated. Scaling is a type of geometric transformation that resizes an image by a specified factor. We can use cv2.resize function to perform scaling. Complete code for scaling using Python. Import cv2, load an image, then define the scaling factors for width and height. Calculate the new dimensions after scaling and then apply the scaling using resize. Display the original and scaled images. In this example, you can modify the scale factor x and scale factor y variables to control how much the image is scaled along the horizontal and vertical axis, respectively. Keep in mind that using values greater than 1 will enlarge the image and values less than 1 will shrink it. Flipping. Flipping is a type of geometric transformation that mirrors an image along a specified axis. We can use the cv2 flip function to perform flipping. Complete code for flipping using Python. Again, it is an import cv2, load an image, then perform horizontal flip, perform vertical flip, perform both horizontal and vertical flip. Display the original and flipped images. With the help of ImShow, you can see the displayed images. In this example, replace path to your image.jpg with the actual path to your image file. The code loads the image and then uses the cv2 flip function to perform horizontal, vertical and both horizontal vertical flips. Finally, it displays the original image and the 3 flipped versions, that is, image performed a horizontal flip, then vertical flip and then both performed horizontal and vertical flips. Shearing. Shearing is a type of geometric transformation that skews an image along a specified axis. We can use the cv2 wrap affine functions to perform shearing. Complete code for shearing using Python. Import cv2, load an image, define the shear factor, get the dimensions of the image, define the shear matrix. Apply the shear using the functions sheared image is equals to cv.to wrap affine image, shear matrix width and height. Display the original and sheared images. You can modify the shear factor variable to control the amount of shearing. Positive values will shear the image to the right and negative values will shear it to the left along the x-axis. The y-axis is not sheared in this example, but you can modify the shear matrix to introduce vertical shearing as well. Perspective transformation. Perspective transformation is a type of geometric transformation that changes the perspective of an image. We can use the cv2 get perspective transform and cv2 wrap perspective functions to perform perspective transformation. Complete code for perspective transformation using Python. Import cv2, load an image, define the source and destination points for perspective transformation. Calculate the perspective transformation matrix. Apply the perspective transformation using wrap perspective. Display the original and transformed images. Note: ensure that points 1 and points 2 are defined accurately to achieve the desired perspective transformation effect. Affine transformation. Affine transformation is a type of geometric transformation that preserves parallel lines in the image. We can use the cv2 get affine transform and cv2 wrap affine transform to perform affine transformations. Complete code for affine transformation using Python. Import cv2, load an image, define the source and destination points for affine transformation. Calculate the affine transformation matrix, apply the affine transformation using wrap affine. Display the original and transformed images. Make sure that the points 1 and 2 are defined correctly to achieve the desired affine transformation effect. The point should form a non-collinear triangle in both sets. Non-affine transformation is a type of geometric transformation that does not preserve parallel lines in the image. We can use the functions CV to find homography and CV to warp perspective functions to perform non-affine transformation. Complete code for non-affine transformation using Python. Import CV2, load an image, define the transformation points. For non-affine transformation, you will need to manually specify the destination points that correspond to the source point in a non-linear manner. Calculate the perspective transformation matrix. Apply the non-affine transformation using warp perspective, then display the original and transformed images. Keep in mind that defining non-affine transformations can be more involved and may require a deeper understanding of the specific transformation you are trying to achieve. The code provided gives a general structure, but you will need to adjust the points according to your desired non-affine transformation. Image warping. Image warping is a technique used to create a new image by transforming an original image using a specified transformation. We can use the CV2 warp perspective and CV2 remap functions to perform image warping. Complete code for image wrapping using Python. Import, load an image, define source and target grid coordinates. Generate a mesh grid for interpolation. Perform interpolation to warp the image. Create the warped image. Display the original and warped images. Perspective correction. Perspective correction is a technique used to correct the perspective distortion in an image. We can use the get cv2.get perspective transform and cv2.warp perspective functions to perform perspective corrections. Complete code for perspective correction using Python. Import CV2, load an image, define the coordinates of the corners of the region you want to correct. Define the desired output rectangle for perspective correction. Calculate the perspective transformation matrix. Apply the perspective correction using warp perspective. Display the original and corrected images. Make sure to replace the values in source points with the actual coordinates of the corners of the region you want to correct and specify the desired width and height in the DST points. Note that perspective correction may require accurate selection of source point and results may vary depending on the complexity of the correction. Edge detection. Edge detection is a technique used to identify the edges in an image. We can use CV2 canny function to perform edge detection. Complete code for edge detection using Python. Load an image in grayscale. Apply Gaussian blur to reduce noise and improve edge detection. Perform canny edge detection. Display the original image and the edges. You can adjust the threshold 1 and threshold 2 parameters of the CV2 canny function to control the sensitivity of edge detection. Smaller values result in detecting more edges, while larger values result in detecting fewer edges. Note that edge detection may vary based on the specific image and its content. You might need to fine-tune the parameters and consider other pre-processing steps based on your image characteristics. Contour detection. Contour detection is a technique used to identify the contour in an image. we can use the CV2 find contours function to perform contour detection. Complete code for contour detection using Python. Import CV2, load an image, convert the image to grayscale, apply Gaussian blur to reduce noise and improve contour detection. Perform Kenny edge detection, find contours in the edges image. Draw the contours on a copy of the original image. Display the original image and the contour image. Contours are drawn in green with a line thickness of 2 pixels. You can adjust the threshold 1 and threshold 2 parameters in the CV2 Kenny function and modify other parameters in the contour detection process to suit your specific image and requirements. Feature detection and feature matching. Feature detection is a technique used to identify the unique features in an image. We can use the CV2 sift and CV2 surf functions to perform feature detection. Feature matching is a technique used to match the features in 2 images. We can use the CV2.match template and CV2 flan based matcher functions to perform feature matching. Complete code for both using Python. Import CV2, load 2 images. Initialize the sift detector, find the key points and descriptors with sift. Initialize the flan matcher, match descriptors, apply ratio tests to filter good matches. Draw the matches, display the matched image. Please note that this example demonstrates one approach to feature detection and matching. Other feature detectors and matchers like ORB and brute force matcher etc. are also available in OpenCV, and the specific approach may vary based on use case and requirements. Object detection. Object detection is a technique used to detect the presence of an object in an image. We can use the CV2.cascade classifier function and the HAR cascades to perform object detection. Complete code for object detection using Python. Import CV2. Load the HAR cascade classifier for face detection. Load an image. Convert the image to grayscale. Perform face detection. Draw rectangles around detected faces. Display the image with detected faces. You can adjust the scale factor, minimum neighbors and minimum size parameters in Detect Multi-Scale to control the sensitivity and accuracy of the object detection. Note that the HAR cascade classifier is particularly suitable for detecting simple object patterns like faces, eyes and more. For more complex object detection tasks, consider using deep learning based models like YOLO or FasterRCNN. Optical flow. Optical flow is a technique used to track the movement of objects in a video. We can use the CV2 calc optical flow PYRLK function to perform optical flow. Complete code for optical flow using Python. Import CV2, load 2 consecutive frames from a video or camera feed. Create an empty mask to draw the optical flow vectors. Calculate optical flow using Lucas-Kanaday method. Select good points, draw the optical flow vectors, display the result. Please note that you need to have a video file with motion to observe the optical flow effect. Background subtraction is a technique used to separate the foreground objects from the background in a video. We can use the CV2 background subtractor emoji function to perform background subtraction. Complete code for background subtraction using Python. Import CV2. Initialize the background subtractor. Open a video capture. Apply background subtraction. Apply morphological operations to remove noise. Find contour of moving objects. Display the result. Morphological operations are a set of operations used to manipulate the shape of an image. We can use the CV2 erode, CV2.dilate, CV2 morphology functions to perform morphological operations. Complete code for morphological operations using Python. Import CV2, load an image, apply thresholding to create a binary image. Define a structuring element for morphological operations. Perform morphological operations. Display the original and morphologically processed images. You can adjust the size and shape of the kernel and the number of iterations for each operation to achieve the desired effects. Conclusion. Basically, geometric transformations are powerful techniques that can be used to manipulate images in various ways using Python and OpenCV. We can easily perform a variety of geometric transformations such as translation, rotation, scaling, shearing, affine transformation, perspective transformation, homography transformation and image registration. Each transformation has its own advantages and use cases, and by understanding them, we can create visually stunning images and achieve our desired results. In this lecture, we have covered the basic theory behind geometric transformations, their applications and examples of how to perform these transformations using Python and OpenCV. With these tools and techniques at our disposal, we can continue to explore and push the boundaries of what is possible in image manipulation and computer vision. What are the outcomes? The outcomes of learning about geometric transformations using Python and OpenCV include the ability to manipulate and transform images in various ways such as translation, rotation, scaling, shearing, affine transformation, perspective transformation, homography transformation and image registration. The understanding of the theoretical principles behind these transformations including matrix operations, coordinate systems and transformation matrices. The ability to apply these transformations to real world problems and applications such as image recognition, computer vision and machine learning. The ability to use Python and OpenCV to perform these transformations efficiently and effectively, and to understand the different functions and tools available in the OpenCV library. The ability to optimize and fine tune these transformations to achieve the desired results, including adjusting parameters such as the angle of rotation, the scale factor and the point of transformation. The ability to work with different types of images including grayscale and color images, and to understand the differences between them in terms of how transformations are applied. Overall, learning about geometric transformations using Python and OpenCV can help us to develop a deeper understanding of image manipulation and computer vision, and can provide us with the skills and knowledge necessary to solve complex problems in these fields. Applications of geometric transformations. Geometric transformations play a crucial role in various fields and applications where the manipulation and analysis of spatial data are essential. Where the manipulation and analysis of spatial data are essential. These transformations involve altering the shape, size, orientation and position of objects while preserving geometric properties. Here are some notable applications of geometric transformations. First, computer graphics and animation. Geometric transformations are the backbone of computer graphics and animation. They enable the creation of visually appealing graphics, special effects and realistic animations. Transformations like translation, rotation, scaling and shearing are used to animate characters, simulate motion and render 3D scenes. Image processing. In image processing, geometric transformations are employed for tasks like image resizing, cropping, rotation and warping. These transformations are vital for enhancing image quality, correcting distortions and aligning images for further analysis. Computer aided design, that is the third application. Geometric transformations are fundamental in CAD software, where engineers and designers use them to create and modify designs. Transformations enable users to manipulate 2D and 3D objects, apply deformations and visualize how changes affect the overall design. Medical imaging. Geometric transformations are utilized in medical imaging for tasks such as aligning images from different modalities, correcting distortions and re-registering images for comparison or fusion. These transformations are crucial for accurate diagnosis and treatment planning. Robotics and autonomous vehicles. Robots and autonomous vehicles rely on geometric transformations for navigation, obstacle avoidance and path planning. Transformations help robots understand their surroundings and calculate movement and orientation adjustments. Graphical information system. In GIS applications, geometric transformations are used to align and overlay maps and spatial data. This facilitates analysis, visualization and decision making in fields like urban planning, environmental management and disaster response. Augmented reality AR and virtual reality VR. Geometric transformations are essential for creating immersive AR and VR experiences. They allow virtual objects to be aligned, scaled and oriented in the real world, enhancing the user's perception of the digital content. Art and design. Artists and designers use geometric transformations to create visually appealing compositions, patterns and designs. These transformations provide a versatile toolkit for manipulating shapes, colors and arrangements. Video game developments. Geometric transformations are integral to video game development, enabling game designers to create dynamic environments, characters and interactions. They contribute to the realism and interactivity of modern video games. Satellite imaging and remote sensing. Geometric transformations are applied in satellite imaging and remote sensing to correct distortions caused by Earth's curvature and sensor characteristics. This ensures accurate measurement and mapping of the Earth's surface. Video compression and streaming. Geometric transformations are used in video compression algorithms to reduce data redundancy and enhance compression efficiency. Transforms like discrete cosine transform and applied to transform video frames into a frequency domain, enabling more efficient storage and transmission. Archaeology and cultural heritage. Geometric transformations aid in the reconstruction and preservation of archaeological sites and cultural artifacts. 3D scanning and modeling techniques utilize transformations to create accurate digital representations for documentation and restoration purposes. Industrial manufacturing and robotics. Geometric transformations play a crucial role in manufacturing processes like CNC, machining and 3D printing. They are used to transform digital designs into physical objects with precision. Robots in manufacturing often use transformations to manipulate and assemble components. Satellite orbit determination. In satellite navigation and orbit determination, geometric transformations are employed to calculate positions and trajectories of satellites and other celestial bodies. These transformations help ensure accurate positioning and navigation. Computer aided tomography and medical imaging reconstruction. In CT scanning, geometric transformations are used to reconstruct 3D images from 2D X-ray slices. These transformations enable the creation of detailed volumetric representations of internal body structures. Physics and simulation. Geometric transformations are used in physics simulations to model real-world phenomena. They are employed in simulations of fluid dynamics, structural analysis and particle interactions among other fields. Virtual fitting rooms. Retail applications utilize geometric transformations to create virtual fitting rooms, allowing customers to visualize how clothing and accessories will look on them without physically trying them on. Architectural visualization. Architects and designers use geometric transformations to create visualizations of buildings and structures. These transformations help convey design concepts and explore different perspectives. Character animation in movies and games. In animation production, geometric transformations are applied to create lifelike character movements and expressions. Transformations bring characters to life by controlling their poses, facial expressions and gestures. Astronomy and astrophysics. Geometric transformations are used in celestial coordinate system to map positions of stars, planets and other celestial objects. These transformations aid astronomers in understanding the universe's vast expanse. In conclusion, geometric transformations find application in a wide range of domains from entertainment and design to scientific research and engineering. Their versatility and impact make them an indispensable tool for manipulating spatial data and enhancing our understanding of the world around us. Thank you.